So we will be starting chapter 6 with metal. Metal have several characteristics, which is the first one is high density, the second one is medium to high melting point, the third one is medium to high elastic modules, the fourth one is reactive, the fifth one is ductile, and lastly, good heat and electric conductor. So next, metal and alloys. Have you ever think why metal and alloys are mostly used in production? This is because alloying elements can be added to a metal to improve number of properties, which are to improve hardness, to improve strength, to increase the corrosion resistance, to increase ductility, and to improve toughness. Next, metallic material can be divided into two parts. The first one is ferrous metal and alloy. The second one is non-ferrous metal and alloy. So the first one is ferrous metal and alloys. From the names itself, ferrous metals, it means that it contains large percentage of iron. Besides having iron, it also have carbon. For example, ferrous metal and alloys, there are steels which contain high purity of iron, and we have cast iron, which is some crude and low quality ferrous metal. So the second one is non-ferrous metals and alloys. So as it says from the name, non-ferrous metals, it does really means that it do not contain iron. So for example, for non-ferrous metals and alloys are aluminium and copper. Further explanation on what is ferrous and non-ferrous metal can be get from the next video.
Today I will be explaining the difference between ferrous and non-ferrous metals in an hour-long documentary. That's right, unlike other channels, I like to keep my answers short and sweet. The answer is pretty simple. Ferrous metals are metals that contain iron. So, ferrous metals include mild steel, carbon steel, stainless steel, and cast iron. So, if ferrous metals means metals that contain iron, non-ferrous metals must mean metals that don't contain iron. So, examples of non-ferrous metals are aluminium, copper, titanium, zinc, and tin. All of these examples are non-ferrous, and therefore they do not contain any iron. So to recap, ferrous metals are made with iron. Examples of it include carbon steel knives, stainless steel pans, and cast iron frying pans. And non-ferrous metals do not include iron. An example of a non-ferrous metal is copper. Copper is used in electrical wirings. The reasoning for this is because it's a very good electrical conductor. This is one of copper's many great properties. Another example of a non-ferrous metal is aluminium. Aluminium is used in applications that desire lighter materials. These include aircrafts, for instance, which need to save as much weight as possible. A good property of aluminium is that it is very lightweight in comparison with steel. That's the end of this episode, and please subscribe for more. Thank you.
So here we can see that there are several differences between ferrous metals and non-ferrous metals. So the first one is magnetic properties. For ferrous metals, it does attract magnet, while non-ferrous metals do not attract magnet. The second one is cost. The non-ferrous metal costs much higher than the ferrous metals. The third one is resistance to rust or corrosion. Ferrous metals do not have low resistance to corrosion. This is because the iron itself tend to rust when it is exposed to water and air. And lastly, for recyclable, both ferrous metals and non-ferrous metals are available for recycle. So there are several effects of carbon on steel. The first one is it could help increase hardness, increase strength, and increase the brittleness. But it is also could reduce the weldability, reduce plasticity, reduce ductility, and reduce the air corrosion. So here we have two types of iron, which are cast iron and wrought iron. For cast iron, it is an alloy of iron which contains about 2 to 4% of carbon by weight. Thus, it has high carbon content. The production of the item for cast iron is by molding. So, cast iron also always have been known with brittle, castable, and strong. So, for example, of cast iron that has been melted, put into a mold, and allowed to solidify is pan that we always use for cooking purposes, such as in the picture. Thermal processing of metals. The thermal processing techniques can be used to control microstructure and mechanical properties of metal alloys.
We have a substantial investment in the latest computer-controlled vacuum heat treatment furnaces that provide precise and repeatable heating and cooling cycles to achieve the best metallurgical results with minimal distortion. Various furnaces are available, up to an individual capacity of 4 tons, for optimal processing of components from small fastenings to large forgings and fabrications. Heat treatment under high vacuum ensures that there is very little surface oxidation, so processed components leave the furnace almost as bright and unblemished as when they were entered.
The first one is quenching. Quenching is a heat treatment method that quickly returns metal to the room temperature after it is heated above its supercritical temperature. The quenching process stops the cooling process from altering the metal's microstructure. It is mostly applicable to steels. The second treatment is annealing. Annealing is a heat treatment that which material is heated above its upper critical temperature for an extended time period, followed by cooling to room temperature at a relatively slow rate. The annealing has 3 stages, which is the first one is heating to the required temperature, followed by soaking it at a constant temperature, and lastly by cooling. The annealing heat treatment, it causes changing in microstructure to the metal. Further explanation and will be shown in the next video on how annealing process happen. There are several purposes of annealing. The first one is to relieve internal stresses. By annealing, it helps to avoid the distortion and cracking of the metals. Second one, it helps to improve machinability. A softer and a more ductile material is easier to machine in the machine shop. Lastly, refinement of grain. After some types of metalworking, particularly cooling, the crystal structures are elongated.
Ceramics. Ceramics comes from the Greek word meaning pottery. Ceramics are inorganic and non-metallic group of materials whose ingredients are clays, sands, and feldspar. The atoms in ceramic materials are held together by chemical bond. The two most common chemical bonds for ceramic materials are ionic or covalent bonds. Ceramics are good electrical and heat insulation properties of ceramics include low density, high melting point, very high elastic modulus, reactive, and brittle. Type of ceramics are glasses, clay-based, which is traditional ceramic, engineering ceramic or advanced ceramic, cement and concrete, rocks and materials, ceramic composites. Examples of new engineering ceramics are carbides, nitrides, and borides.
This week, Lab TV travels to NAVC Carter Rock in Bethesda, Maryland, to meet an engineer who creates some really hot materials called ceramics.
All of you know about household ceramics, the things you see in your house. Your house might have bricks on it, you have dinner plates, you have coffee mugs, there might be tile on the wall or on the floor, and everybody has in their house this huge piece of ceramic, and that's the toilet. It's the biggest piece of ceramic that anybody has in their house.
Ceramics are also used in places where you might not see them. They're called technical ceramics.
Technical ceramics are used to make capacitors. It's in almost every electrical device that you have. They're used to make fiber optic cables which transmit light. Maybe the most famous example of a technical ceramic is the space shuttle tiles, which coat the entire bottom surface of the space shuttle. Those ceramics are there to protect the shuttle when it's coming back into the atmosphere from burning up.
Ceramics are strong, hard, and durable. They have very special properties that give them lots of advantages over some other materials.
A ceramic is usually a very high melting material. It has high hardness, and it has a lot of brittleness, but it is made from a metal combined with another element, and the other element is usually oxygen, carbon, nitrogen, or boron.
Probably the best thing about ceramics is their high melting temperature. That lets engineers use them in places where even metals would melt.
The kind of materials we work with would have melting temperatures from about 1700 degrees C up to about 3000 degrees C. So your oven at home could probably get to 250 degrees C. When you stand by a campfire and see those glowing embers on the bottom, that temperature is about 1200 degrees C. And the highest temperature that you would see at home is that filament in that light bulb is way above 2000 degrees C.
Another great property of ceramics is their hardness.
Ceramics are very hard, and based on Mohs scale of hardness, the softest material is talc, the hardest material is diamond. The materials that we work with are very close in hardness to diamond. If you need to cut something, you put ceramics on it and it can grind and cut almost anything.
Ceramics can also withstand chemicals and erosion, but they're not perfect materials. Unfortunately, they can be brittle and they can break.
We try to make ceramics that try to get rid of the brittleness. That's the biggest drawback of ceramics. So we don't want to take something that we make, drop it on the floor and have it break.
Dr. Zakowski and his research team use a process called sintering to create their ceramics.
At our laboratory, we use primarily dry powders. We mix 2 or more different chemicals, then we put it into a mold and press it into a shape. It's usually in the shape of a disc, a thin disc. Then we take this disc and put it into a furnace. That's the most important part of making a ceramic, is to put the material into a furnace and put tremendous heat on it. You have to heat it between 1700 to 2200 C.
They heat the disc to just below its melting point. That causes the powders to stick together and form a strong crystal structure. Now it's a ceramic.
Ceramics are going to be with us forever, and they're going to be used in many, many applications. We are particularly looking at ceramics for Navy applications in engines. We want to put ceramic materials in there that allows the engine to operate at higher temperatures and derive greater efficiency from the fuel.
Dr. Zakowski and his team have received 20 patents for their work, and they're still trying to create new and better ceramics.
That's exactly right, and that's part of our job. And everything that we make here is very new. It's never been done before, and that's the exciting part of what we do.
To find out more about ceramics and their amazing properties, check out labtvonline.org.
Classes of ceramics. The first one is traditional ceramics. Traditional ceramics are clay-based. The nature of this final product is determined by the composition of the clay used, the type of additives employed, and the firing temperature. Examples is clay, which is hydrated aluminium silicate, silica, flint or quartz, and feldspar or potash. The applications of traditional ceramic are in building, bricks, sewer pipe, drain tiles, and roofing tile.
Process of manufacturing ceramics is simple. In this section, I will explain you the process and raw materials used for manufacturing ceramics. I will also explain you how non-porous ceramics are made. The main ingredients in making ceramics are clay like kaolinite and bentonite, flint, white clay, quartz and feldspar. The commonly found ceramics which you are familiar with are earthen pots. When clay is mixed with water, clay becomes flexible. It acquires plasticity. Then desired shape is given to this smooth mixture of clay and water. After giving shape, it is time to harden it. This can be achieved by removing water from the material. Hence, the wet clay after shaping is heated in furnace. This will eliminate water from the clay partially. Actually, this process leaves behind invisible holes on the surface of ceramic. When water is escaping from the clay, it leaves behind very tiny holes. This is the procedure to make ceramics. Not only clay is used as raw material, but other earth-like materials such as kaolinite and bentonite are also used as a substitute for clay. The ceramic artifacts made by this process can break easily. This can be prevented by adding non-clay materials like flint and quartz to the mix. Flint and quartz are different forms of silica but do not absorb water. Since they do not absorb water, they also do not get transferred on heating and hence do not shrink. These ceramics are hard and do not break easily. But these artifacts are porous like normal ceramics which are made only with clay. Non-porous ceramics can be achieved by adding substances to clay mixture which are hard and water repelling. One such material is feldspar. Feldspar gives a smoother, glossy finish to the ceramics. So, raw materials should be chosen depending on the desired quality in ceramics. Porous, non-porous, hard ceramics can be made using appropriate raw materials. Once the appropriate raw materials are chosen to get the desired finish, next step is shaping these into needed form. This is followed by drying and firing of the shaped article which stabilizes the shape. Thus, the sequence shaping, drying and firing is the characteristic of all the ceramics.
The second classes of ceramics is advanced ceramics or engineering ceramics. Advanced ceramics are not usually made of clay. Industrial inorganic chemicals such as artificial raw materials with particular features necessitate more complex processing. Examples are oxides such as alumina and zirconia, non-oxide carbides, nitride borides, and silicide. For example, silicon nitride and silicon carbides. Composites is also an example of advanced ceramics. Application of advanced ceramics is in fridge magnet, aerospace, automotive, which is above component, electronics, and personal protection. The third classes of ceramics is glasses. They are non-crystalline silicates that incorporating with oxide, especially calcium oxide and many more, that affect glass characteristics. Their application is in container, lenses, and smartphone screen. By applying the appropriate high temperature heat treatment, the majority of inorganic glass can be transformed from non-crystalline to crystalline. The most common uses for these materials are tableware, kitchenware, oven window, TV glass, automotive glass.
Ivoclar Vividend is proud of its IPS E-Max and IPS Impress glass ceramic blocks. They are used to fabricate long-lasting, aesthetic, high-quality restorations. Every day, our employees strive to ensure a consistently high production standard. They measure and mix colors to achieve just the right color composition, and they repeatedly check it. Only when the correct basic powder mixture has been achieved is it molten into glass at a temperature of 1,500 degrees Celsius. The glass melt is quenched in a cold water bath. After cooling, the glass is finally ground again and sintered in the furnace. This is how glass is transformed into glass ceramic. In ball mills, the glass ceramic is ground into extremely fine powder. It goes without saying that at this stage of the process, close monitoring is crucial. In the formulating room, hundreds of shades are created. 1/1000th of a gram can determine whether the desired hue is perfectly attained or not. Employees compare the shaded products with the corresponding shade standard and check their fluorescence. Once the powder has been correctly prepared, CAD blocks are produced by means of a press procedure. In this form, they are still called green bodies because they have not been fired yet. Once the blocks have passed the quality check, they are fired in the vacuum furnace at around 1,000 degrees Celsius to become IPS impress blocks. In another production line, IPS Emax blocks are manufactured. This process also requires monitoring down to the last detail. By means of a complex procedure, the blocks are partially ceramized. The outcome is the characteristic blue IPS Emax ceramic blocks, which have gained us millions of satisfied customers around the globe. High-quality materials combined with the latest technology and the enthusiasm for what we do. Our glass ceramic blocks set new standards in digital dentistry. True to our motto, passion, vision, innovation.
The fourth classes of ceramics is clay, one of the most widely used ceramic raw materials. It is a natural mineral created by weathered rock. The whiteware ceramics become white after the high temperature firing. The properties are greatly improved, such as imperviousness to fluids, low electrical conductivity, chemical inertness, and they can be molded into complicated shapes. Application of clay is in porcelain, pottery, tableware, and sanitary ware. The fifth classes of ceramics is refractory materials. A refractory materials is a ceramic materials that can tolerate high temperatures for an extended period of time. For example, a mineral that is restrained to decomposition by heat, pressure, or chemical attack. The term is most typically used to describe a mineral that retains strength and form at high temperatures. For example, is silica and alumina system.
Fire, both worshipped and rightly feared. But without fire, life as we know it would be impossible. Our civilization, our modern lives are created out of fire. Look around. From fire came the first tools of civilization. Pottery and ceramics, plows for farming, weapons for security. Then came the machines and marvels of the Industrial Revolution, the steamships, railroads and automobiles, all made with fire and powered by fire. It's even more incredible today. Cities spreading to the horizon, mass transit, aviation, wondrous electronics, medical marvels, and technologies of the future stretching to the universe. The amazing 21st century, built with iron and steel, aluminum, cement and concrete, and glass, all dependent on fire. But how do we control the fire? What is the secret of taming the flame? The answer is refractories. From a word meaning durable or stubborn, refractories are ceramic materials which are designed to withstand the very high temperatures encountered in modern manufacturing. They line the hot surfaces found inside many industrial processes. Refractories contain the heat and protect processing equipment from the intense temperatures of molten materials and superheated gases. From 1,000 degrees Fahrenheit to 4,000 degrees and higher, refractories protect the industrial processes that serve mankind and make civilization possible. But they are not just used for handling molten metals and ores. Refractories are essential to the manufacture of petrochemical products and the refining of gasoline. They can be found in your family room fireplace and your neighborhood pizza parlor. From flower pots and tableware to porcelain toilets, bathtubs, and sinks, to today's 21st century technology. There are thousands of uses for refractories and thousands of different refractory products. So what are refractories? Refractories are produced from natural and synthetic materials, usually non-metallic, or combinations of compounds and minerals, such as alumina, fire clays, bauxite, chromite, magnesite, dolomite, silicon carbide, zirconia, and many others. Minerals must meet exacting specifications to ensure the durability and effectiveness of the final product. Mined and transported from around the world and right next door, these raw materials from the Earth's crust are then put through a variety of processes designed to enhance their resistance to heat. Giant crushers begin the manufacturing process to transform the materials to ingredients necessary to produce refractories. The raw feed is screened and sized to ensure uniformity. Tons of materials move through sophisticated physical and chemical processing. The raw materials may be heated in giant industrial furnaces to drive off unwanted constituents and begin the necessary chemical reactions. Materials are then combined in exact proportion to meet specified formulas based on the particular application and the characteristics needed. Tons of material every day. Throughout the process, constant monitoring and testing ensure quality control. After mixing and blending to precise requirements, the subsequent manufacturing process can differ significantly. Refractory products are generally divided into two broad categories: preformed shapes and unformed compositions, generally called specialty or monolithic refractories. And then there are refractory ceramic fibers. Refractory ceramic fibers look similar to residential insulation, but insulate at much higher temperatures, up to 3,000 degrees. Bricks and shapes are the more traditional form of refractories, and historically have accounted for the majority of refractory production. Refractories come in all shapes and sizes. They can be pressed or molded for use in floors and walls, in interlocking shapes and wedges, or curved to fit the insides of boilers and ladles. Refractory bricks are usually manufactured using continuous assembly line operations, which ensure consistency and standardization of size and quality. Shapes can be manufactured in quantity or made one at a time for very specific applications. The variety of refractories reflects the wide range of the processes in which they are used. They can be very big or very small, depending on the application. Examples of such products are nozzles and lances for spraying and injecting materials in hot environments, runners, troughs, and gates for transporting and controlling the flow of molten materials. After they are pressed and formed, most bricks and shapes are then subjected to high temperatures over hours or even days to heat treat the materials and complete the necessary physical and chemical reactions needed in a finished refractory product. Heat treatment is done in large industrial furnaces and ovens, usually called kilns, which may be designed to operate continuously or intermittently. Tunnel kilns can be hundreds of feet long and hold dozens of cars. This ensures a continuous process and the efficient use of energy. Bricks and shapes are loaded on cars similar to small railroad cars, and then the cars are pushed into the front end of the kiln. As one car enters the kiln, one car exits the kiln at the back end. Periodic kilns are typically used to process small quantities of materials or large odd-shaped products. They are loaded when cool and then heated to a specified temperature for the time required. Material is removed after the kiln is cooled and the cycle is then repeated. Some refractory applications simply require low temperature treatment to set a chemical bond prior to installation and use. Throughout the manufacturing process, constant monitoring is required. Temperature, chemistry, and engineering are all essential to guarantee performance. Testing and more testing, repeated again and again, to ensure the quality and integrity of the final product. Because of the ease of application for new installations and repair work, monolithic refractories now account for about half of refractory use. Monolithic refractories are generally sold as dry mixes. Various raw materials are sized and blended in large mixers to a specified formula and consistency. The material is then bagged and shipped for use. Some are packaged very much like concrete mix you might find in a hardware store. Monolithic refractories may be poured or pumped into place, sprayed onto surfaces, rammed, or applied with trowels or other tools. They can be precast into predetermined shapes, providing additional flexibility in application and use. Refractories. From the dawn of time to mankind's reach for the stars and beyond, we have relied on refractories to tame the flame. From the first tools to marvels not yet imagined, refractories make it possible.
The six classes of ceramic is abrasives, used to wear, grind, or cut away other materials. Diamonds, both natural and synthetic, are utilized as abrasive. However, they are relatively expensive. The more common ceramic abrasives include silicon carbide, tungsten carbide, aluminum oxide, and silica sand.
Which abrasive grain can represent the ultimate performance and stronger cutting ability, higher grinding efficiency and longer lifetime? Most people today will say ceramic abrasive grain. In the past 40 years, ceramic abrasive grain has been the highest performing grain with the newest technology, and its characteristics of self-sharpening ability has drove the performance of conventional abrasive products to their highest levels. Why ceramic abrasive grain is so special? We will show you through this video, but first, let's reflect on the history of abrasive grains. The use of abrasives goes back almost since the beginning of recorded history. During the earliest period in ancient Egypt, craftsmen began to use stones to polish jewelry and vases. A 13th century document describes ancient Chinese used of natural gums to fix seashell to parchment, which is considered the earliest form of sandpaper. Ancient Greeks extracted quartz from sandstone to grind wood and metal. Most of the early abrasive materials were natural, they occurred in natural deposits and can be mined and processed for use with little alteration. It was until 19th and 20th centuries, the Industrial Revolution spurred the modern advancement in abrasive materials. In 1891, synthesized silicon carbide was first invented in an electronic furnace by American chemist Edward Goodrich Acheson, with its properties such as hardness was enhanced. Following the development of silicon carbide, synthetically manufactured fused alumina was invented. For decades, The electrofusion process was utilized to fulfill the world's needs for abrasive grains. In 1954, the first synthetic diamonds were made in General Electric's laboratories, and that revolutionized the industry and set a milestone of superabrasive. Superabrasive had superior hardness and again greatly elevated grinding performance. The question is that it has extremely hard cost, which made them not widely used. The next step in material advancement came in 1971. Norton Company introduced a fused abrasive grain produced by fast cooling a molten mix of aluminum oxide and zirconium oxide, which is zirconia alumina. The extremely rapid solidification processing of zirconia alumina made this abrasive grain have a microstructure, which had significantly higher performance than the traditional, fused, large crystal aluminum oxides. This new grain demonstrated the importance that microstructure plays in the performance of an abrasive material. Researchers recognized that if controlling the microstructure of abrasive grains could lead to such large performance increases, there could be a competitive advantage in developing new abrasive grains having microstructures engineered for abrasive performance. The breakthrough in the history of abrasive development was in 1981, when 3M researchers developed a technology for the production of abrasives grains using the sol-gel method, which is called Cubitron. And this is the first commercial ceramic abrasive grain. By that time, the first generation of ceramic abrasive grain had outperformed the typical fused alumina in many applications. The birth of ceramic abrasive grain resulted from the continuous pursuit of sharpness, hardness and grinding performance for abrasive grains. In the next video, we will introduce why this material is so special and what development occurred in ceramic abrasive grains. To know more about ceramic abrasive grain, you can subscribe JCT Abrasives YouTube channel. See you in the next video.
Fabrication of ceramics. Processing of ceramics takes place through powder metallurgy (PM) techniques. There are 4 basic steps of processing. The first one is raw material preparation. The second one is forming and shaping. The third step is thermal treatment by drying and firing, or sintering. The fourth step is the final forming. Sintering has the greatest effect on the properties and is subject to the greatest amount of control. Thermal treatments of ceramics. There are 3 thermal treatments of ceramics, which is drying, firing, and sintering. The purpose of drying is to remove water, and it is carried out at or below 100 degrees Celsius. The layer size and the spacing will decrease. Firing. In firing, temperature raised to 900 to 1400 degrees Celsius. Meanwhile, in sintering, a process which small particles are bonded together by solid-state diffusion at very high temperature, but below the melting point of the compound. Porous contact turns into dense product. Mechanism of sintering. Sintering occurs during firing of a piece that has been powdered brass. During the initial sintering stage, nag forms along the contact region between adjacent particles. In addition, a grain boundaries forms within each nag, and every interstice between particles becomes a pore. As sintering progresses, the pores become smaller and more spherical in shape. Vitrification. Some ceramic products, such as porcelain, contain a glass phase. When the ceramics is fired, a process known as vitrification takes place, whereby the glass phase liquefies and fills the open spaces between the particles. When the body cools, the glass solidifies and acts to bond the unmelted particles together.
Alright, now let's talk about polymer. What is polymer? Polymer is basically consists of many monomer that is usually made of a hydrocarbon, which is a hydrogen and also a carbon. Next, the properties of polymer. We have four properties, which is very low density, have low melting point, and low elastic modulus, and also ductile and brittle type. Polymer can be classified as two things, which is plastic and also an elastomer. Right. In plastic, we can say that we have two types, which is thermoplastic and also thermosetting. Right. For the thermoplastic, the polymer is that require heat to be shaped, and also after cooling, the shape is formed. Alright, this type of polymer can be reheat and reformed a number of times without significant change of material properties. Next is the engineering thermoplastic. Why we use thermoplastic? Alright, firstly, thermoplastic is well known as has a low density plastic. Next is it also a high in solution. It also has low tensile strength and also a very good corrosive resistance. Right. The example of thermoplastic is such as nylon 66, polyacetal, polycarbonate, polyester, and polysulfone. Alright. Other than that, polymer can be classified as thermosetting plastic, right? Right. Thermosetting plastic is a polymer that is formed into a permanent shape. Right. This type of polymer cannot be remelt or reformed, as it cannot be recycled also. Right. This polymer is usually made of a carbon networking with covalent bond nitrogen, sulfur, and also other atoms in structure. Right. The reason why we use thermosetting is it has high thermal stability, high rigidity, resistant to creep, and also deformation under load, and also lightweight with a high electrical and thermal insulation. The thermoplastic and also thermoset can be differ by as thermoplastic has a properties of low density and low rigidity, soften void heating, and also has low thermal stability, while the thermoset has high tensile strength, do not soften with heat, and degrades rather than melted. It also has high thermal stability, high rigidity, and also high dimensional stability. Right. The example of thermoplastic in our daily life is polyethylene, PVC, and also polypropylene. Alright, for the thermoset is vulcanized rubber, alright, polyester resin, and also the ceramic. Now we will talk about the elastomer. Elastomer is also known as a rubber. Why? It's because a polymer that is classified as elastomer has a properties that can change when stress is applied, and also can return to its original form as the stress is removed, right? You must wondering, what is vulcanization? Vulcanization is a process of heating rubber with sulfur. Why we do this? Because we want the rubber to be more harder and stronger, but also less elastic. Now, as you can see in this picture, we have a raw rubber that being heated in sulfur, producing a vulcanized cross-linkage rubber, right? If, as you can see at below, we have two polymer of rubber that's been, after being heated in sulfur, the sulfur is cross-linkage both of the polymer rubber, and this is why the vulcanized rubber is more harder and also stronger.
Vulcanization of rubber. Now, natural rubber is soft, sticky, and has less tensile strength. Now, to make the natural rubber more strong, tough, and elastic, it is vulcanized. Charles Goodyear discovered the process of converting natural rubber to more strong and elastic form and called the process vulcanization. Let me explain you how it is done. Natural rubber is mixed with 3 to 5% sulfur and is heated at 100 to 150 degrees Celsius. It forms cross-linking of cis-1 4-polypropene chains through disulfide bonds, SS. Wide range of physical properties of rubber can be obtained by controlling the amount of sulfur in the process of vulcanization. Rubber made with 20 to 30% sulfur is hard. 3 to 10% sulfur is little harder and is used in making tires. Low sulfur rubber is made with 1 to 3% of sulfur and is used in making rubber bands. Structure of vulcanized rubber is given under cross-linked polymers.